Hey guys, that's a video of our last part, our last topic in this chapter 14, pressure in liquids, gases, and solids. Okay, this is our last bit, pressure in gases. Pressure in gases is whenever gases are, or just let's go to laser pointer. Okay, whenever gases are trapped, then they will be able to exert some pressure on their containers, just like our atmosphere, which is filled of oxygen and nitrogen. And as they are trapped in our atmosphere, they start exerting some pressure on us, which we call atmospheric pressure. All right. And the leading pioneer behind that is Mr. Torricelli. Torricelli, an Italian scientist and physicist, he invented this barometer. A barometer is this device that measures the atmospheric pressure. It measures the value, it gives a value, it quantifies the atmospheric pressure. And the atmospheric pressure is the result of air pressuring on us over here on the surface of Earth. Okay, and what he's done is something ingenious. He has used liquids and mercury in this case to figure out the pressure of a certain gas. And what he did was the following. He just placed mercury in a basin over here, and then the atmospheric pressure forced mercury to go into this tube, which he first removed air from, and then the atmospheric pressure from all ends, all sides of this basin forced mercury to rise to a certain level. In standard atmospheric pressure, standard condition, the atmospheric pressure is somewhere around 760 millimeters of mercury, or 76 centimeters in this case. All right? How he calculated and figured out that is as such. If we consider that to be the basin, the container that has mercury, okay, and mercury has risen over here to this height, okay, let's label those 2 points by A and B. And the pressure at point A is due to everything above it, and above point A is what we call the atmospheric pressure. And the pressure at point B is due to everything above it, and above it is this bit of mercury and vacuum. So P at A, to start with, is the same as P at B. So going over here, PA equals to PB. Why? They are at the same level and in the same liquid. They belong to mercury. P at A is the atmospheric pressure. P at B, we've just said it's pressure of trapped mercury and vacuum. So if you equate those, we end up having the atmospheric pressure is only equal or equates to this atmospheric to the pressure over here. And the pressure over here is the pressure by trapped liquid. And the pressure of a liquid is nothing but rho GH, as solved previously. And the density of the liquid used inside is that of mercury, 13,600. G is given as 10. And the height he just measures from here to here, and he found to be 76 centimeters, converted into meters. That would yield 100,003 Pascal. So it could be measured in millimeters of Pascal of mercury. It could be measured in millimeters, in centimeters, in meters, whatever unit you wish of mercury. So the atmospheric pressure is assimilated to millimeters or meters, a length of mercury. All right. This is how Torricelli figured out the atmospheric pressure. So now whenever we deal with atmospheric pressure, we need to deal with Torricelli's barometer, and that barometer usually has mercury. It could have contained any liquid whatsoever. You could have replaced mercury with water. However, water is way lighter than mercury, so water will rise to a height of somewhere around 10 meters in that tube, which was impossible to attain. So he used a dense liquid, making it harder for the atmospheric pressure to lift it. All right? Now we deal with manometers. Manometers are devices that measure the pressure exerted by trapped gases. So to figure out what's a manometer, this is a manometer. To figure out how it works, we get an empty U-tube. We fill it with a liquid of known density, just like water, for example. And then let's assume we inflate this balloon with CO2 and place it over here. And as we place it over here, that level will change. It will rise from one end and dips from another end. If such is the case, then take a look at the seesaw. CO2 has exerted a pressure more than the atmospheric pressure. Why? Because water dipped from this end and rose from that end. Now, how to calculate the pressure of this CO2 on the inside? To figure out the pressure of CO2, this is what we do. We take 2 points, B and C, on the same level. Okay, B is the point of separation of this liquid water and CO2, and C is the point which lies on the horizontal. And then we say PB, the pressure at point B exerted, is the same as the pressure at point C. Okay? Why? Because they are located at the same level and in the same liquid. The pressure at point B is due to everything above B. And everything above B is nothing but the pressure of CO2. Now the pressure at point C is due to everything above it, which is a bit of mercury, or water, sorry, trapped over here, and the atmospheric pressure. So to figure out the pressure of CO2, it's the same as the pressure of water inside and that of the atmosphere. The pressure of water is given as that of a liquid, so it's density rho times G times H. And that of the atmosphere, we need to use a what? A barometer, Torricelli's barometer, that has mercury on the inside. Alright, and this is how we figure out. And that is an example over here. Take this manometer, which is the device to use to measure the pressure of the trapped oxygen on the inside. Alright, the pressure at point A equals to the pressure at point B, as we've said before. Why? Because they are located at the same horizontal level and in the same liquid, water. The pressure at A is due to everything on top of it, which in this case is oxygen. And now the pressure at B is due to everything above it, which is the pressure of water exerted and the atmosphere, water and the atmosphere. Now the pressure due to water is given by rho times G times H. Rho is given as 1,000. Even if you were given as grams per cc, centimeter cubed, you have to change that into kilogram per meter cubed. So we just multiply by 1,000 and we get that, times G, which is 10, times the height of water. In this case it's 5 centimeters, we have to change into meters, so that would be 500 Pascal. Now this is the pressure trapped by water. Now the atmospheric pressure, and to calculate the atmospheric pressure, we agreed we need to use a barometer. And the barometer, let's assume that Torricelli's barometer indicates 75 centimeters of mercury on the inside. And 75 centimeters on the inside, once again, it's rho times G times H. Rho, the density of mercury, is given as 13.6 grams per cc, in which case we have to change to kilogram per meter cube, times G times H, which is 75 centimeters. Again, we have to change that into meters, and that amounts to 102,000 pascals. And now P at of oxygen equals to this and that. You just add them and you equate the pressure exerted by oxygen, which is more than that of the atmospheric pressure, because if you take that balance over here, that seesaw, this pressure, so we notice that oxygen wins and the atmospheric pressure loses to oxygen. Okay, that would be the end of pressure in gases and the end of this presentation.